Okay. So it's my pleasure to introduce Joshua San Miguel. He's here from University of Toronto. He's going to talk about overcoming fundamental inefficiencies in representations of data in conventional architectures. And his work really spans a pretty broad range of architecture, from approximate computing through network on chips and all sorts of different things. So take it away.
Thank you. Thank you for that. So in this talk, I'll be discussing how we overcome fundamental inefficiencies in the way we represent data in our modern systems. So there are three emerging trends that are posing considerable challenges to our systems and architecture. The first is that in our everyday lives, we're relying more and more on these small devices. Whether it be your smartphones, your smartwatches, your smart home technology systems. And in these systems, first of all, energy constraints are becoming far more strict, more so than ever before, and that any inefficiency in our hardware now can seriously impede our productivity and our quality of life. And the second thing, though, is that with a lot of these systems, what's common is that they actually tend to process naturally approximate information, whether that be noisy sensor data, user subjective input, or multimedia content. What happens, though, is that our conventional systems, they just weren't built for this. Our conventional systems provide this precise, exact computing platform that wastes considerable amounts of energy for this naturally approximate information. So this has led to increasing interest in what is known as approximate computing. That is, if you take your conventional architectural space, we're typically bound by this Pareto frontier of efficiency, where you can't reduce your execution time without compromising your energy, for example. However, with approximate computing, the idea is to simply add a third design axis of error, where now, by exploiting the approximate nature of your applications and allowing for some acceptable quality loss, we can now reach new levels of efficiency that were never possible before. The second trend is that now it's all about data. We have an abundance of information. We're looking at nearly 200 zettabytes of digital data in the world by 2025. What this means now is that our applications, whether they be running in your data centers or on your personal devices, are becoming far more data intensive and more memory bound, less compute heavy than what we're used to. So now, as before, our conventional systems just weren't built for this. We're now incurring the high cost of accessing data from off-chip memory, which is orders of magnitude greater in latency and energy than simply accessing your floating point arithmetic or your private on-chip caches. So we now need fundamental new ways to better utilize our off-chip memory bandwidth. And the third trend is that CMOS scaling is no longer favorable. In the last decade, we hit thermal and power ceiling, which now limits how fast we can clock our chips, how much of the chip can be fully powered on or active at any moment in time. Where it's actually projected that in the 5 nanometer process down the road, when you think about it, in terms of full active area, we're only looking at about a fifth of the chip. And as before, our systems just weren't built for this. We now need fundamental new ways to better utilize our on-chip resources and be more selective in the way we schedule our compute and the way we move and store our data. So in my research, what I look at is I sort of reframe these problems. Because at the heart of these challenges is what I consider a fundamental lack of data context in our hardware representations. So in the first one, our systems waste energy on naturally approximate information because we lack a notion of functional context. So what type of information is encoded in the bits? If you look at 32 bits in isolation, you can't tell, aside from how the instructions use it, is it a byte array? Is it an integer? Is it some GPS sensor information that I could approximate in some way? Second, I talk about how we need better utilization of our off-chip memory bandwidth because we lack a notion of spatial context. Where is the information located in the data set? Because if we had a better idea of our data structure and our data organization, we could more concisely represent it in our systems. And finally, we need better utilization of our on-chip resources. That's because we lack a notion of temporal context. When is information needed by the application? Because now if we can't power on, we can't run all of our computations simultaneously anymore, but we could be more selective based on the significance of the data that we process. So the key takeaway is, I broke it down into that taxonomy, but the key takeaway is that in our conventional hardware, it typically perceives data as nothing more than bits. But awareness of this data context, if we could exploit it, we could eliminate fundamental wasted energy and better utilize our resources and our bandwidth. And naturally, this notion of data context extends throughout the entire system stack. In this talk, though, I'll explore the inefficiencies and challenges that come due to a lack of data context at the architecture level. But in the future work section that I'll discuss later, I'll discuss how we could explore things lower in the stack, for example, decay and compression and other ideas, as well as exploiting this notion of data context higher levels of the stack. So in this talk, I'll be discussing 3 architectural techniques that address functional, spatial, and temporal context. I'll be discussing them in more of a high-level sense to get the fundamental takeaways of them so that I can spend more time on some of the future exciting research ideas that I have. So the first is this notion of memory value approximation. Here we exploit functional context in order to approximate the values of data in order to improve memory efficiency. This works well with applications like this body tracking application, where given the baseline and given our technique, you see very little difference in the output quality. This is just a simple example. Computer vision is an excellent example of many approximate computing techniques. But let's start with the problem. So take your typical multiprocessor system. Over time, we're executing some application up on the processor core at the top. And then at some point, naturally, we're going to want to access data. So we'll go into our private cache and say we have a miss. What happens now is we have to go traverse through interconnect, traverse the higher level of caches until we get to our off-chip memory. And all of this is orders of magnitude greater in latency and energy than simply having access our private cache. And it is a huge cost that we continue to incur, especially the more data-intensive our applications are. But what's really happening? Like, if we looked at that moment in time, what's really happening right there? And if you ask any architect, they'll tell you, oh, that's simple. It's a load instruction. So an instruction is requesting a memory block. But you wouldn't be wrong, but it's not actually the full picture. Because what's really happening is we're running some application in some system in the real world that's doing something with it. Maybe it's processing GPS sensor, temperature readings, or so forth. So at the end of the day, what is really happening is that instruction is requesting information. And this information just so happens to be stored in a memory block. So now, can we decouple these notions? And for that, I propose this notion of memory value approximation, where you introduce hardware approximators with your private caches so that now upon a cache miss, you could essentially estimate the value that your application wants to process and feed that directly back to the processor core. And now it could continue executing, and off the critical path of execution, you can then incur that high latency and energy of accessing and retrieving the actual value. And you could simply use that now to train that approximator and allow it to better estimate the values of your data in the future. And what you effectively have is this pipeline where the processor will access data from the approximator and continue its execution while in the background and off the critical path, you can go ahead and retrieve the actual values to better train your approximations. And what happens with this now is, if your approximator happens to be accurate enough, you can actually remove fetches from off-chip memory that were never possible before. And all that's possible because now we're able to decouple the fundamental computing on the data from the fetching of that data just by having some notion of the information that we process. So a natural question that comes from this is, okay, so then how we implement this? Can we do it in software? However, when you do it in software, you have to make considerable changes and assumptions in the program code in order to ensure that things work properly. Typically, by doing things at a higher level of the stack, you introduce abstraction overheads, such as virtual to physical address translations. As well, if you're implementing these approximators and they're in software, naturally they're going to end up residing in memory and occupying the processor pipeline as well, which would be counterintuitive considering it's such a fine-grained approximation that you're trying to do. So with hardware, it allows you to get more fine-grained efficiency gains. However, if we're going to do this on hardware, then how can we do it with low complexity and low overhead? So to do that, we exploit a notion of approximate value locality. Just a simple observation in order to reduce the complexity of the hardware that many data values are similar to or can be approximated from previously seen values. This notion that has been exploited before with like prefetching and branch prediction, so that now you could simply use buffers of historical values, and as long as you organize them in a way where you maintain a notion of a context, like where are we now in the program, and then use that in order to go through the historical values we've seen, and then essentially estimate what data values did we see the last time we were here in the program. And you can just do this in order to perform an approximation. Let me, just a very simple example, say we have a miss on address A. So from this, we can then generate some index into our history table given the most recent values we've seen in the processor. Say they're roughly 1, 2, and 3. So this gives us an idea, oh, this is generally where we are in the application. So then we'll use that to index into the table. And then given the values that we've seen the last time we were roughly here, we generate an approximate value and then feed that to the processor core. And now off the critical path, we could request the actual value of A, and when it finally arrives, it's a simple matter of pushing this into the history buffers. So it's a very simple form of training and learning. And this is only a simple example. There's many different ways you could, for example, encode that hash function that indexes. There's many different ways that you could extrapolate and interpolate the values. We found that there are very simple solutions to minimize the complexity of the hardware. And as I'll allude to later, you could actually exploit analog arithmetic and noisy storage in the way you do this, because the branch predictor naturally doesn't affect your program correctness. Because the approximator is already amenable to the kind of approximation and values that you get in your application. Yes?
You motivated this by talking about sort of like sensor node things, where you're pulling in real world data. And it seems to me, I'm just wondering, like, is there a reason to think that you can do this approximation and prediction for real world sensor data? It seems like in that case, oftentimes if you go look at it again, it'll change. And also, especially for sensors, it seems to me like a lot of times what you're interested is when it suddenly changes.
No,
it might be stable for a long time and then suddenly change.
Yeah, no, that's a very good question. There is like just a matter of really depending on the situation. So this is more, that statement I said applying these techniques to like sensor data, it varies depending on the technique. This is more of sort of the way you deal with different computations. Can we predict the way we compute on the data? In a sense, what's the result or sort of this impact? Like in ongoing work, that I don't discuss here, you could sort of exploit the resulting values that you get from the computations and actually directly use that to feed in to this notion of your approximator. So these are values that you would naturally store into memory and then would get incorporated in later phases of the application. But then it's really like a matter of approximating what kind of things that we're going to do. And then here I'll be showing the error energy trade-off that we get from this value approximation technique. This is run with full system simulations, cycle level simulations, and our applications range from computer vision to fluid particle simulation. I'm showing the average error based on application-specific metrics. The lower the better in terms of the error. And on the x-axis, I'm showing approximation aggressiveness. So this is just an abstract concept to remove a lot of the many different design knobs that there are. But the higher the aggressiveness, that means the less fetching, or in a sense, the less training we're doing now. So what happens with this naturally, with less training, you get a modest increase in the output quality of your application. However, the trade-off is that you're able to reduce the average number of fetches that you have at a higher level cache and off-chip memory as well. And it comes to the point that it's just a matter of selecting the design point that best suits your application. We don't want to say that this point is ideal for all cases. We present the results as a trade-off and let you choose the design point that makes the most sense. And what's important is that we also provide hardware mechanisms that are able to disable value approximation and monitors it every now and then periodically to decide whether or not the error is good enough, what's its confidence in the approximations, and can actually disable it if it's not helpful. But as before, it's a matter of selecting the design point that best suits the application or the use case. And for this one here, for example, it's up to 1.4x speed up and 1.5x energy savings and corresponds to this body tracking output that I showed before. But the main takeaway is with memory value approximation, we're able to exploit functional context to decouple the fetching of the data bits from the processing of the information. So the next part, I'll be discussing cache spatial value similarity. Here we exploit spatial context to uncover approximately similar values, and we do this by exploiting the dataset structure in order to save data movement and storage costs. So again, we'll start by highlighting the problem. So we have our chip multiprocessor system. As before, we need better utilization of our off-chip memory bandwidth, and also correspondingly, we need better utilization of our on-chip cache storage, because now our caching is a precious storage in order to alleviate that off-chip memory bandwidth. However, to do this, we ask the question, is there a correlation with where data is located with what value is encoded in that data? So to answer that, we recall that the goal of a processor is to process real-world information, not bits. So what this means, first of all, is that data values can often be approximate and continuous, or smooth in their nature. And secondly, when we encode this in the digital world, these are simply just data addresses represented along a one-dimensional memory space. So if you combine those observations, you could imagine that there is considerable regularity to where values that are similar happen to be located when we flatten them out into one-dimensional memory. So say, for example, we have a three-dimensional data set here where each element, like the one highlighted, maps to a single unique location in our one-dimensional memory space. If we look at adjacent elements along the x dimension, because our data tends to be smooth, we could expect that they're approximately similar in value, and the good news, they also happen to be contiguous in memory. However, if you look along the y dimension, and worse along the z dimension, as before, these are naturally likely to be similar in value, yet now they're not contiguous and they're nowhere near each other in memory. But what we do know is they're separated by a regular stride. That's because of the way the three-dimensional structure was made. So for example, with image processing, if we look at adjacent pixels along a column, we could expect them to be similar in value, but even though they're not contiguous, we do know that they're separated by a stride equal to the image row size. Same thing goes when you're processing any signal in the time domain. You can imagine that you'll find similar values at strides of the signal period. So then, can we then exploit this notion of our real-world data and alleviate some of these costs in off-chip memory bandwidth in our on-chip cache storage? And as before, you could ask, can we exploit this notion in software? As before, you potentially have considerable changes in your software code, or you'd have to make considerable assumptions in them. You have high abstraction overheads. If we're going to do this at the last level cache, you'll pay a big price in having to deal with the virtual to physical address translation and so forth. So then, if we want to do this in hardware, how do we do it with low complexity and low overhead? So to do that, I propose the bunker cache, which is trying to keep as much of the cache architecture left unchanged by simply treating an address x and an address x plus stride as if they're one and the same in the cache indexing structure. So let's take our conventional cache lookup. We have an address x, and we put that through some index function, which then generates a set of tags of different ways. And then we compare that tag with the physical address, and then let's say in this case we find that it exists, so it's a hit. And then we return the corresponding contents of x from the corresponding entry of the data array and send that to the other caches. However, now if we had a lookup for address x plus stride, as we mentioned before, the contents of this are naturally approximately similar to the contents of x. However, it's a unique address, so then when we go and run it through the index function, we'll get a completely different entry, which incurs a miss, and now incurs that off-chip memory cost for a piece of data that we already have similar in value on the chip. And then when we allocate storage for it in our cache, we end up wasting considerable amounts of on-chip cache storage, again, for two values that are naturally similar, yet are now occupying completely wasting our precious on-chip caching resources. So then to address this, bunker cache simply introduces a similarity mapping function. It's a many-to-one mapping function from the physical address space to the bunker address space. So that now, upon a lookup for x plus stride, the mapping can be configured such that the bunker address of x plus stride is equivalent to that of x. So now it's a simple matter of going through the cache architecture in the same way as before. You'll now have an effective hit, which saves you that off-chip memory cost. And now when you allocate data, you end up saving considerable cache storage for the two unique blocks in memory. And now the key is that this similarity mapping is actually very low in complexity and overhead, uses only fixed point multiply add operations. And this is possible because the stride information that I was discussing before could actually be pre-computed, and you can get the reciprocal of this and then save yourself a lot of the compute cycles, which is very important because the mapping function is on the critical path of every cache lookup. And second, you could do all this with leaving the rest of the cache hardware actually left unchanged. So a lot of this technique could be applied with our commodity systems already. And the key thing about leaving the logic very simple is that it could actually be simply disabled if it's not helpful at all. In which case, the similarity mapping would just be a one-to-one mapping between the physical address and the bunker address, and you get the precise execution in the end. So to explore that, again, we ran simulations. We're looking at here application quality. This time, the y-axis is showing the signal-to-noise ratio as a measure of application quality. The higher, the better. And then, again, with an aggressiveness of 1, that is a many-to-one mapping function of 1-to-1, we get the precise result. And then I'm showing in the line here the average of our applications, and the shaded area is the minimum and the maximum of different applications. Yes?
Aggressiveness of 1 here means that you're not doing anything, the mapping function just passes on the physical address?
Yes.
Okay.
It's, so here at aggressiveness, you can think of it as a 1 is a 1-to-1 mapping from the physical address.
The previous graphic, aggressiveness of 1 was That's some approximation, right? Or was that also the baseline?
Yeah, so that's a little confusing there. It was just the different notions of, in that case, for the memory value approximation one, the aggressiveness there is what we define as an approximation degree. So you could think of it as analogous to a prefetch degree. So an approximation, yeah, an approximation degree of 1 implies one prefetch, and one prefetch degree of 1 is prefetch. So you're looking at the varying levels of quality. Again, we present this as trade-offs. There's more details in the paper, but it's a matter of selecting the design point that best suits the application and the use case. That's the thing with approximate computing. There's no real right trade-off in many cases. And I'll discuss this in the last piece of work. But in this case, for example, you get savings in runtime, dynamic energy, and because we're effectively applying a many-to-one mapping function, it's effectively a form of compression. So you get leakage power savings in that as well. Yes?
So could you replicate this by just downsampling your data? Yep.
No, that's a good question. So with that though, it may not be as fine-grained in the granularity that you want. It really depends on the different trade-offs of having to do something in software versus doing and abstracting in hardware. If you do that, again, downsampling the data, for example, if you don't want to change the way your computation works, or you'll have to reason about how your computation reasons about the downsampling. Otherwise, you may also have to reason about what are the implications of that during my page table walks, during the virtual to physical address translation, and so forth. It'll be an interesting thing to explore, the different trade-offs. As with many things with approximate computing, naturally this is arguably anything that you can do in the digital domain in hardware can be replicated and done in software. It's just a matter of the trade-offs, the granularities, and how much of an overhead one introduces over another. As I'm showing here, you could do this with very little overhead in your hardware and really reap the efficiency gains at the gatekeeper of off-chip memory, essentially. And then the way I like to think of it is actually, in terms of data movement, we're able to provide a form of cache prefetching without fetching. Because now a request for address X implicitly prefetches address X plus stride already. And in terms of cache storage, we're able to provide a form of cache compression without actually having to manipulate data values. Because the storage for X plus stride is saved without having to need to fetch X plus stride and read the values, because we're exploiting natural tendencies in the approximate information that we see in our applications.
Is the software configuring the stride here, or is that something that the hardware is going to detect for me? And
That's a good question. So the hardware can detect it for you with overhead of having that initial curve. In a lot of the experiments we looked at, it was a simple matter of just extracting that information from the memory allocation routines in the beginning of your application. So the good news about that is a lot of that stays static because it's really just the dimensionality of your data structures. And you could get that from the malloc libraries that you already run in the beginning. And the last is anytime automaton model. Here we exploit temporal context to provide a new computation model that tries to address fundamental challenges in the field of approximate computing in general. So I call these three challenges holistic quality control, interruptibility, and user flexibility. So I'll discuss those now. So say we have our example application. We have some 3 computations on it, and we have to run the 3 computations in sequential order. And say I wanted to apply approximate computing to this, and I wanted to apply it to that first computation. Okay, so then you take our approximate computing technique. Naturally, they have some runtime quality trade-off to them. So then, okay, let me just tune the quality of that to some quality level that I want and save myself the runtime, like that. And say, okay, let me do the same thing for the second computation. I want to approximate that as well. Let me tune the quality and save ourselves runtime there too. Problem though is, what happens with the final output? You can't guarantee that's going to be acceptable because the quality of the local approximations doesn't necessarily extrapolate to their composition. This is a unique aspect of approximate computing. Whereas with runtime, for example, you reduce the runtime there, you could easily reason about it, the runtime loss, the runtime reduction for the total application. But in terms of quality, it doesn't work that way. Second is the notion of interruptibility. So a big motivation for approximate computing is its use in real-time systems. These are cases where the time constraints can be more critical than the quality of result, automotive systems and telecommunications and so forth. So then the question naturally is, okay, can we apply approximate computing to some general application in a real-time system and have it meet some strict target runtime? Fair and simple, okay. Sounds intuitive. You just take the tuning knobs that you have for each of your techniques, tune them to some quality that matches that runtime, and move on. You've met the strict target runtime. However, in reality, actual runtimes are highly variable, as we would expect. And now, if we were to do this, because the runtime quality trade-offs vary dynamically, can you ensure that you meet the strict time constraint with some acceptable output? Because if this is slightly off and this goes beyond that target runtime, is your output even acceptable at any point from there? And finally, is a more subtle challenge in approximate computing is user flexibility. So that is, as before, if I wanted to tune the quality and apply some approximation to one of those computations, I don't even know what the target quality is. That's because acceptable quality, that notion, varies so much from user to user, and it can't be determined a priori. So how can we possibly deal with that with approximate computing? So for this, I propose the anytime automaton. It generalizes concepts from anytime or iterative algorithms to sort of make sense of all the ad hoc approximate computing techniques that have been proposed in our field recently. So the idea being that here I'm showing application execution. Conventionally, we let our application run, and then we produce one output in the end of our application, which is the precise result. However, the anytime automaton, the idea is to produce intermediate results along the way with increasing quality of time. So then now, this addresses the three challenges, because if I wanted to apply some form of quality control, the final output is available very early on. So you don't tune the quality based on the local approximations, which you can't reason about in the end-to-end application quality, because now the end-to-end application quality is ready for you. So you can do any form of quality monitoring on that. In terms of a real-time system, if we now impose a strict target runtime, we have a large window of interruptibility, where you can now interrupt at any point in this large window and get some decent output that's available already. And finally, in terms of user flexibility, if you provide one result to the user and it's not good enough, it's a simple matter of waiting until it eventually reaches the precise result. So we give the user, we effectively put the onus on the user to define their level of acceptability. And we give them a simple rule of thumb. It's a simple matter of waiting longer if you want better quality. So then, how do we do this? So to do this, you have to break your program into sort of a data flow style model. I'll discuss the differences later, where each node is a computation, each edge is the data dependence. And the computations can be as fine-grained as a single instruction or as coarse-grained as a full-blown kernel. And now the natural question is, for a general application, and I want to approximate it, how do we create that effect of improving accuracy over time? Well, you could ask, okay, is the whole end-to-end application an anytime algorithm? It is a very complex question to answer, very difficult, and if you want to generalize it, it's a very difficult game to have to reason about every possible application and making it anytime. But instead, what you could do is exploit the slur of fine-grained approximate computing techniques that have been proposed, and then instead of producing a single result in each of these nodes, you can then just apply the approximate computing techniques in intelligent ways to give that effect of improving quality over time. And now it's very heterogeneous, because if this node can use, for example, some form of approximate storage, this node can use a different form of approximation, you could apply them differently as long as you apply them in this anytime way. And from this, I call this form of a data diffusion model instead of a data flow model. So, like for example, we have our input. In the beginning, our first node can already compute, before it computes the final result, can already compute some approximate result. And it could feed that to the child, and the child can now work on that parent's approximate result, while in the background, the parent can work on producing a better approximate result. So now you've extracted a form of pipeline parallelism with this anytime approach, where now, effectively, the computations propagate until you get the final output available early. And if it's not acceptable enough, it's a simple matter of letting the application run longer, and effectively data is diffused, or precision is flowed through the model from left to right until you finally get the precise result in the end. So then, the natural question that comes after that is, given those nodes, how do we now apply our fine-grained approximate computing techniques in a way that has that increase in quality over time? So there are many different approaches. For the purpose of the talk, I talk about the general approach, which is to reorder instructions based on each data element's significance to the quality of the final result. So this is the notion of temporal context. If we can get an idea of which data needs to be processed first and reorder the computations that way, we can get this anytime approach. So I'll just discuss some very simple examples. Say we want to apply this anytime approximation approach to a reduced precision dot product of fixed point values. So this breaks down into 3 multiply operations. And if we were to cut this off at any moment in time, it's not any time because the final result wouldn't be ready at that point. However, the idea is to realize that each of these multiply operations is any time in themselves. You just break them up into the partial products from the most significant bit to the least significant bit. So now if you break up all the multiply operations and then reorder the entire dot product to move all the most significant partial products to the beginning, you can now cut off the computation early on and get some decent result for your approximation in the end. Another approach is, say, you're doing some form of output sampling. In this case, we're going to generate an image from some input set. If we did the conventional sequential permutation, row major order of accessing our elements, this is not any time because if you decide to cut it off halfway, your final result's not going to be ready. It's not going to be acceptable. However, by simply changing the permutation in the way you compute from your sampling, when you access the first 4 elements with a tree permutation, you get a 2x2 approximation of your output. And when you access the 16 elements, you get a 4x4 approximation, and so on. So you effectively get increasing resolution of your result until you finally get the precise result, and you've never had to do any redundant work. You just changed the ordering in the way you sampled your elements. So the general takeaway is that you could create that effect of improving quality over time by simply reordering the processing of the data elements. That's that notion of temporal context. So here I'm showing some experiments with one of our benchmarks in 2D convolution. These are experiments were done on real hardware because we just wanted to demonstrate the impact on quality that we can get and how the quality performance trade-offs happen even on real hardware. On the y-axis, I'm showing the quality, which is signal-to-noise ratio again. And on the x-axis, I'm showing the runtime of a system normalized at the baseline without the anytime automaton. So the first thing you'll notice is very early on, at only 10% of the baseline runtime, we're already able to generate some approximate result. It's a very crude approximation, not very good to look at, but at 25% of the baseline runtime, for example, we already get a fairly decent approximation of the final result. And then if that's not acceptable, it's a simple matter of waiting longer until you eventually get the precise result in the end. The first thing you'll notice, though, is that getting the precise result with the anytime automaton is nearly 2 times the baseline runtime. And this is simply because we're running this in real hardware as a fair comparison, but I told you that the fundamental principle is reordering of the data elements. And what happens there is it really has a huge impact in terms of caching and cache locality. And that's where that huge loss is. But the good news is it's highly deterministic. So if we apply more sophisticated mechanisms with, as I'll discuss later, looking at anytime architectures for this, because it's deterministic, I believe you could easily bring that down to the baseline runtime and get this effect of improving quality over time without any overhead in terms of the runtime. But the general notion is that you provide some execution model where how acceptable the output is scales directly with how much time is expended. So I like to call that a form of hold the power button computing, where instead of pressing the power button, waiting, and getting the precise result in the end, you hold it for as much time and energy so you expend just the right amount of time and energy for just the right amount of acceptability you want and the quality of your final result.
How many data flow nodes are in this benchmark?
Sorry?
So you have this idea of you have data flow nodes, right? And you're sort of doing any time on each node.
Oh, yeah.
So like how many nodes are here? Like how deep is that?
That's a good question. I believe that was one of the smaller ones, but I think only like 4 nodes, and only one of which or 2 of which we were applying the approximation for. So that also adds a little bit of an overhead because there's other things you have to do, like sort of organizational stuff that you maintain precise. However, they just run sort of whenever they can. The chunk of the computation, much of that was able to be approximated and is the reason why we have that effect.
Do you have a similar idea for the energy cost of doing the approximation, right? Because obviously time is longer. Is energy sort of proportional to time in this case?
It really depends on the cases. So for the 2D convolution, for example, it would be as well. The trade-off then comes with...
You're thrashing in your cache hierarchy, right? So any time that you're missing there, it's going to cost you a lot more energy.
Yes. But given, for example, just theoretically, we had the architecture built for it, you could account for this because it's deterministic accesses. You could alleviate that. The issue then comes with sort of computations that you have that aren't well amenable to this model, where the most basic worst case is you'll have to run different versions of your computation with varying levels of approximation, and in which case you're effectively, there's redundant work there by its nature. We could, hopefully you could still exploit things in the hardware, for example, reuse of data that you wouldn't have gotten before. They'd all be, instead of cold misses for all of them, you could reuse the data and sort of exploit that, but there's a fundamental redundancy there. So the key is sort of, we've looked at the recipe, identified properties of different computations to identify the ones, how to frame your computations to map that. So for example, like the fixed point reduced precision dot product I showed and the sampling, for example, have in theory no redundant work. It's just a matter of pure reordering the computations, but not everything is that friendly. So it becomes a trade-off of that. Like an example is like loop perforation. One of the examples where with loop perforation, it's like splitting up different loop iterations. However, you can't, depending on increasing the granularity or making the finer granularity of loop perforation, it doesn't necessarily map well. You may have to do redundant work and other things.
And then one other question on the,
Yeah.
so if you have a graph, your graph of nodes, it's fine to say this first one, the first node is this 2D convolution, and I'm gonna sort of, keep increasing the resolution of my output. But do I have to recompute all of the follow-on nodes starting from scratch, or can I actually sort of only take the new pixels that I've calculated and apply those selectively to the following transient?
Yeah.
Like, how does that actually propagate?
That's a good point as well. So that's also something that I didn't get to discuss here. So we looked at properties of how to pipeline. Basically, that pipeline could be asynchronous or synchronous. That's the way I define the terminology, where either they're based on redoing the whole data if that's the way to reach the precise result in the end, or actually only operating on updates. So a lot of it comes with, you could actually do this with a lot of different computations where you're just pushing updates through. And that has very interesting impacts to it because depending on the values of the updates, you could reason about how much computation needs to be done and so forth. That's where the data diffusion term sort of came from, where updates sort of flow through as opposed to direct data explicitly flowing through the model. Yeah.
I mean, do you have a sense for how easy or hard, like how different is the programming style to sort of make that work versus taking an application that I have and saying, I want to do this computation in an approximate way? Like, it feels like now I have to actually go and recode sort of each of the steps of my algorithm to basically process data in a very, very different way than I had before, right?
So one thing would be in the future hoping to automate the process. So at the coarse granularity, if you're making your computation nodes at a coarse granularity, which we did in the experiments, I don't see, it's not too much of a burden to have to do it. At the end of the day, what's neat about it is it's really optimization. Because if you wanted to use it, it's naturally because you want to ensure that you get the precise result in the end. And because the model is set that way, you can guarantee that. It's just a matter of how ugly the curve is to get there. If you think about it, I mean, if you think in discrete steps, the original computation was anytime already. You just had no result and then precise result in the end. So everything else that comes with it doesn't harm your correctness anymore. It's really whatever work you're willing to put into it. So even the process of building the anytime feels anytime, because it's whatever work you're willing to put into it to make the curve nicer is sort of the trade-off you're imposing on yourself as well. So in the future, we expect it to be automated, where we can basically give some notion of things. We provide some pragmas of cookie cutter template types of computations that we support, and you put them through with some form of precision and stuff like that. So in the future work, naturally this notion of data context will span throughout the entire system stack. In the short term, I'll be describing some ideas. For example, at the architecture level, there's still fruitful work in anytime architectures, as I call it. So say we have your typical microarchitecture, we have your beefed up, out of order, superscalar core. What happens is in a lot of cases, we actually tend to have low utilization in these processors because due to limited instruction level parallelism. We have more data-intensive applications. They're more limited by the memory. So now we have a lot of idle resources. Our application only uses the blues parts. But what you could do is actually use these idle resources to effectively improve the quality of results by applying this notion of anytime approximations. You could apply them at a fine granularity because a lot of the approximate computing techniques I've proposed are fine in granularity. And now this effectively extracts a form of anytime instruction level parallelism, or best effort instruction level parallelism. If you have the resources available, great, you could use them to improve your quality of results. If not, then you go on and you proceed the way it is. It's really just a best effort approach for whatever resources you have. And this applies to more broad coarse-grained fabrics. For example, with the catapult, you have your network of FPGAs, you have some application mapped out to the logic here. And if you have any excess utilization and resources to spare, you could actually allow for best effort parallelism via the anytime approximations that I talked about, where these could be approximations of improving quality in order to minimize the tail latency of your computation. Or if it's not for approximate computing, you could have surrogate algorithms. And this is for precise computing now. So say your sort. There are different sorting algorithms. Theoretically, quicksort is better than bubble sort, for example. But depending on changes in the environment and the system, or depending on the way your initial values are set up, one may actually yield a faster result than the other. And this is not approximate computing error, this is precise. So with whatever resources you have to spare, in a best effort manner, you use them to compute surrogates and minimize your tail latency for your computations. Looking down lower in the system stack, we look at ideas that I call decaying memory compression and pseudo-approximations. So with decaying compression, you take your typical single-level memory cell, you store it with some, say, resistance value here, encodes the value of 0, for example. But with new memory technologies like phase change memory, we have multi-level cells where you can store 2 bits and even up to 3 bits in some cases. This comes at a trade-off where now you incur an error because of the larger read-write margin and the levels of the way you're encoding your data in each memory cell. But it also comes with interesting phenomenon like resistance drift, which now monotonically increases your resistance to the point where a lot of your data values in your memory cells actually tend to work towards 0 in this case. So now you have overheads of error correction to have to deal with these error margins, as well as scrubbing in order to have to fix drifted values. So then, can we exploit the data context, knowledge of the information that we process, that maps well in order to reduce the overhead and error correction and scrubbing? So then you can imagine that notion of spatial value similarity that I discussed exists in your memory as well. You have your memory blocks for address A, B, C, and D. And you can expect that in a lot of cases we have a lot of similar values. And this is a high storage cost for approximately similar data and having to do this. But then what you could do now is the fact that the values are similar, what you do know is that the deltas tend to be small. So now you could encode the values as offsets to some base, which is the base A, and apply them and store them in these multi-level cells, control the granularity and the precision to save yourself significant storage, depending on how much approximation you're willing to tolerate. But what happens nicely is you have a nice relationship with dealing with drift, because now the blocks that are more important, naturally you could expect the ones to be high reuse, so those would be scrubbed more and would have less impact of drift. But then in the worst case scenario, if you drift your value to 0, you're just drifting a delta to 0. So then in the worst case, you're just saying that if that drifts to 0, it just means that D is equivalent to A. So now by changing the encoding of your data, you're able to exploit the natural analog tendencies of your underlying memory technology. And another follow-on to this in the hardware layer is exploiting this notion for what I call pseudo-approximate computing. That is, you have your typical chip multiprocessor, and what happens is we have a lot of components in the hardware, like your branch predictor, your prefetcher, your placement policy, route arbitration, and so forth, that are naturally optimization or prediction-based. So now, what you could do is apply a lot of these notions of approximate computing using fuzzy storage, analog arithmetic, and race logic to these components without harming correctness at all. And a lot of them are very amenable to these ideas. For example, with that notion of drift that I discussed just now, works very well for any form of data, or like with the replacement policies that has a notion of time, timestamps, your LRU replacement, and so forth. Other things is you can exploit things like race logic, where you encode data and computation as timing delays. And that maps well to things like your branch predictor, your prefetcher, where you have notions of confidence. And instead of storing those as saturating counters and then having them win in terms of the prediction, you can encode these implicitly in the terms of the timing delays. And the key is that this now allows for applying approximate computing techniques with no impact on your application correctness. And then moving up the stack, we can then look at what this notion of data context and how that the implications of this in your multi-threading and synchronization. For example, as we have more and more threads and higher parallelism, what happens is for even a tiny critical section, we have this large locking overhead, a major performance bottleneck in having to deal with synchronization, even though the underlying critical sections tend to be very small. Then you think about it is that these critical sections really are just a form of information sharing, fundamentally, right? And they tend to be very small because that's the way they're by design. We don't want to hold the log for that long. There's really just supposed to be some regular rudimentary operation in order to facilitate information sharing. Now, given that, we could exploit a lot of the notions I was discussing before where because this is just information, can we estimate that information? And now, if these are regular operations, can we exploit that value locality to effectively approximate or memoize these critical sections and do this in sort of a throttle or sampled manner and save ourselves significant synchronization overhead to improve the scalability of these massively parallel applications. So then, I discussed all these little short-term ideas, but in the long term, the idea is our system stacks are built upon these ISAs, instruction set architectures. And I've moved towards more of a notion of a DSA, a data set architecture, because right now hardware doesn't interpret data bits on their own. It only interprets them based on how instructions use them. So we lack a lot of the data context, and because of the trends we're seeing in more specialized computation and more data intensiveness, we want to be able to better explicitly provide the context for the data and switch it to a model where instead of random access data and explicit instructions, to more random access instructions and explicit data. Because right now, hardware doesn't interpret data bits on their own. So for example, if we compare the ISA and the DSA for functional context, with the ISA, hardware knows exactly which functional unit to use for an instruction because it has the opcode. But it doesn't know the function of each data element. Is it purely numerical? Will it be used as a memory address later? I could see you performing integer adds and multiplies, but I can never guarantee that you're not going to dereference this later. So I can't do anything about that. In terms of spatial context, with the ISA, hardware knows that within a basic block, adjacent instructions in memory will always execute together. But in terms of data, it doesn't know if adjacent data elements will be accessed together. It can never make that guarantee. And in terms of temporal context, hardware knows that all instructions in a basic block will always execute in sequential order. In the same way, if we look at the data, we have no idea in what order data elements will be accessed, and we have absolutely no guarantee for that. Then the idea is, because we're more data-oriented now, and because we have room for specialization of our computations, mapping well to sort of the reconfigurable logic we have in Catapult, can we have more of these DSA-based architectures, where the data context is the one that's made explicit? And then naturally, this is going to impact the entire system stack. It'll be very interesting to see what implications this has down in the hardware layer and all the way up in the system stack. Because at the end of the day, what we do here in the architecture is provide this digital layer that, for whatever reason, sits on top of an analog physical layer and below an analog user layer. So then, can we address these fundamental inefficiencies that arise from this? So to summarize, we looked at the notion of data context, particularly in architecture. I looked at them based on temporal, functional, spatial context. That was the taxonomy I provided. And the key is that by addressing these notions of data context in architecture, it actually spans very broadly in the different ways that you get efficiency gains, whether it be in compute, data storage, or in data movement. And they could be as coarse-grained as looking at the priority levels of packets into your network on chip, or as fine-grained as exploiting the spatial context of the data you process in order to get even better branch prediction. And finally, I'd like to acknowledge all the help I got from my advisor, Natalie and Ray Jerger, collaborators from Cornell, IBM, INRIA, NVIDIA, and University of Washington, and some generous funding from IBM in Toronto. And with that, thank you. Yes.
We kind of touched on this during lunch, but so I like the idea of this data-centric view, but I have the sense that anytime there's some structure, let's say temporal, it's a stream of images in the video, or spatial, an image itself, and you have pixels and JSON, we kind of already do something about it. There's these domain-specific ways where in the picture, if I see that there's a ton of similar areas in the picture, I already encode them. No one really stores raw images with photography. You usually have some compression that already takes advantage of that. Same goes for MPEG, for instance. You don't really encode each frame, you encode how things move around.
Yeah, exactly.
So how much opportunity is left? If you start specializing for each domain to do this more generic underlying thing.
No, that's a very fair question. It's a good question. And it's not so much, I see it not so much as specific application domains, but sort of the environments that we're going to see computing, because computing is ubiquitous now. And you're processing streams of like sensor input somewhere on like some tiny device on your bracelet and other things.
Imagine, sorry, could have
Yeah.
from the sensor example, actually, I was thinking there, like, if I know that a sensor is usually going to be sending the same thing, I assume sooner or later, a sensor vendor or someone will optimize that protocol to only send you, a very short bit sequence if it's the same and something longer.
Right.
So we kind of naturally try to minimize the information. You don't want to have redundancy. Anything that can compress, you kind of naturally compress things that you can detect. I don't know if internally in a large-scale system, if there's areas where we are very inefficient, and maybe that's where this thing kicks in. But that's kind of...
Well, in that sense, you could think of it in that. So, I mean, that really motivates that natural. You could see that as like a means of co-design, right? I mean, the sensor is effectively still part of the hardware fabric, you could think of it. And then it's a matter of what tunability do you have, dynamic on the fly. If you do provide these forms of sampling mechanisms, what implications does that have on all layers of the system stack? And does it really satisfy the requirements of the guy all the way at the top? And if so, how does he bring that down as well? So it's a matter of these little questions, I guess the little trade-offs and implications these have vertically on the system stack that are going to be interesting to see. But you're right, in specific application domains, there are already algorithmic techniques. And then it's a matter of looking at, are they complete? And by complete are they vertically complete? An algorithm proposed at the top level, if we run it on this system, is it as efficient as it could possibly be, or is there more to it as well, right?
This open discussion, I don't know the answer to this, but anytime, like before you had the stride example, right? If I had to go to put that in by hand, then I kind of have knowledge about this data because it's repetition, and there is something that I can do better. This kind of also goes back to Adrian's question, like, would it be worth to just go back and restructure my data representation to use something different? I think it would be really cool if you had something that automates this process. I don't know if it's a small machine or something.
That's definitely, I mean, just because I'm sort of like the work was bound to the architecture layer doesn't mean that a lot of the techniques will. As I said, with anything that you exploit in the digital layer and architecture can naturally be exploited elsewhere. And it's a matter of the trade-offs there. In that case, the trade-off would be more of the direct implications you have to the programmer. Can they even, I mean, is it worth it for them to make a change of code? What's the cost of a change of line of code versus an abstracted way of doing it, automating? And maybe if automating is the way to go, and if the overheads of that in software are fine, that's great. Or if the overheads in software themselves could be alleviated by providing dedicated hardware, even better. So you have a synergistic approach as well.
Yeah, I mean, it'd be interesting, you take the example of a video codec, right? There's huge amount of engineering time put into basically developing, figuring out what all the blocking looks like and how to compress each frame and taking advantage of, spatial and temporal locality and things like that. If you could basically take that raw video stream and apply your techniques, which are sort of inherently trying to figure out all those manual optimizations that people are making, that would be a really interesting sort of case study, right? It's like, how close can this automated hardware-based approach get to this hand tuning that's being done to sort of compress and deliver video
Yeah, it'll be interesting to see. And then I guess following from that too is like, can you then exploit also other analog characteristics by doing that in the hardware that you wouldn't have otherwise been able to exploit doing it in software, right? So things like those aspects. More questions?
All right. Well,
Thank you guys. Thank you.